In Chapter 4, we will concern ourselves with solving differential equations. In particular, we will be talking about two types of differential equations that we can solve exactly and numerical methods for how to approximate solutions to the equations that we cannot find exact solutions to. Let's first of all start by reviewing the simplest differential equation that we've already studied and the solution to it that we have already seen. So again, this equation states that the rate of change of a function is proportional to the function itself, and it has a unique solution that the function that satisfies this equation is in fact the exponential function. How about other types of differential equations? The first thing we can do is the simplest, and that is to check whether a given function satisfies a given equation. So that means, again, thinking about, for example, how if I ask, does x equals 2 satisfy the equation x squared equals 4, I would simply be plugging it in and seeing whether or not the equality holds. Similar to this here, the solution to a differential equation is a function, and it is in fact a solution if the equality in the differential equation holds. Differential equation is an equation that involves a derivative, so the first thing I can do is take a derivative of this expression and then check whether or not it satisfies this rule. So let's take a derivative of our y here. So I have that y prime, and then this case, or in this case here, the function is quite complex, so we're going to have to think about the chain rule as applied to this function. Outside function is my degree. It will come down to the front, and the power will get reduced by 1. 1/2 minus 1 is -1/2. And then I have to follow up by the derivative of the inside, which in this case is simply 2. Now, I can see that I can actually simplify this derivative by, for example, canceling out the two 2's. And I can even then make it a little more easy to digest sort of on the eyes if we bring the negative power down to the denominator. So this is the same as 1 over 2t plus 1 to power 1/2. Now the idea is, let's say I've simplified it, is this the same as the differential equation given, or is this similar, or is this definitely not satisfied? So in my differential equation, I have that y prime is equal to 1 over y, whatever y happens to be. And once I took the derivative, I can see that y prime is equal to 1 over 2t plus 1 to power 1/2, which is in fact y. So this is indeed 1 over y, and then I can clearly see the same differential equation as I have above. So this function does satisfy this differential equation. For the next one, we're asked to check whether a negative exponential function satisfies differential equation y prime equals 1 minus y. So again, I'm simply going to first of all take a derivative of this function. Notice that I move freely between the notation dy by dt and y prime as long as the independent variable with which I'm taking the derivative with respect to is understood. So for this one, the derivative is, I'm going to leave y not alone because that's a constant. The derivative of e to the negative t is simply itself. And then I have to multiply by the derivative of the inside, which in this case is minus t. So the derivative of that is minus 1, and I can put that in front of my entire function for to simplify this a little bit. Now, what does that actually tell me? This expression I've already seen before. This is the same as this expression here, which is equal to y. So what I have in this case is that y prime is actually equal to minus y. Again, that is because this entire expression is simply y, as we can see here, and then I have an extra minus in front. We're asked whether or not this function is a solution to this equation, and this equation states that y prime needs to be equal to 1 minus y. Well, clearly, minus y is not the same as 1 minus y, which means that this particular function is not a solution to this particular differential equation. So again, checking whether something is a solution or not is simply figuring out the derivative of this and seeing if the derivative in fact satisfies the equality given in the differential equation. Making up differential equations is actually a bit easier because you get to decide on the relationship that is to be satisfied. So let's see here, we have three different examples. We'll start off with, we would like the function y equals x squared to satisfy some kind of differential equation. Well, I can simply take a derivative of it, and I will have y prime equals 2x, and there you go. This is the differential equation that is satisfied by this function. So this is a solution. Now there may be other solutions, but this is most definitely one of them. I can even take the second derivative, and then I will have what we call second order differential equation that involves higher order derivative. So in this case, y prime is equal to 2. And again, I am guaranteed that this function satisfies this differential equation because I derived it from the function itself. Let's see what we can do in terms of differential equations for y equals e to the x. So for example, y prime is equal to e to the x. This function is, the derivative of it is itself. So I can actually rewrite this even simpler because e to the x is just y itself. This differential equation can be written as y prime equals y. And in fact, because any derivative, second, third, fourth, and so on, of e to the x is just itself, it is a solution to lots of really simple-looking differential equations, such as y double prime is equal to y, y triple prime is equal to y, and whatnot. See if you can do this for sine of x in terms of the differential equation that involves y prime and differential equation that involves y double prime. The other types of questions we can ask are of this particular kind. Find the value of a constant a so that a given function y equals e to minus x is a solution to the given differential equation y double prime minus ay prime is equal to 0. So here, the approach is exactly the same. If I would like this function to be the solution to this particular equation, it means that when I plug it in, the equality actually has to hold. Now, this equation involves y double prime and y prime, so first I have to calculate those. If I start off with y equals e to the negative x, then y prime is minus e to the negative x because of the chain rule, and y double prime is going to be e to the negative x again, because I'll be taking the derivative of this, and then the chain rule will give me a derivative of the inside, which is one more time going to give me the negative in the front. So what I'm going to do now is take all this information and plug it in to the differential equation that's given. Y double prime is then, as given in my little table, y double prime is e to the minus x. So I'm going to have e to the minus x minus a times y prime, which is negative e to the negative x. And according to my equation, this whole thing has to be equal to 0. Let's see if I can simplify this. I'm asked for what values of a does this actually hold, so I'm trying to find all possible values of a that will make this equation true. If I open up the brackets here, I'm going to get e to the negative x, and then I see that the two minuses will cancel each other out, and I'm going to get plus a e to the negative x. I can factor out e to the negative x, and I'm going to have 1 plus a in the bracket left. This is a nice looking equation because I now have a product of two things that is equal to 0. A product is only ever equal to 0 if one of the two things equals to 0. So I can break this equation into two pieces. Either e to the negative x is equal to 0 or 1 plus a is equal to 0. Well, let's attack them one at a time. E to the negative x is equal to 0. That can never happen. An exponential can never be equal to 0 or go below it, so this part produces no solutions. Whereas 1 plus a equals to 0 when a is equal to negative 1, and that is going to be my only possible value of a which will give me that this function satisfies this particular differential equation. Now, it is one thing to check whether a given function is a solution to a given differential equation. What we've done before in the last couple of slides is just plug it in and see whether equation holds or not. It is a whole other thing to actually finding a solution to the equation we've never seen before. So we're going to start with a fairly simple form here. dy by dt, or y prime, is equal to 1 minus y. What we're going to do is introduce a new variable z to replace the entire right-hand side. Okay, so let's call this z and then see whether that helps us in any way. It's nice that the right-hand side is now one small variable, one concise variable. However, the problem now is that the left-hand side talks about the derivative of y, while the right-hand side talks about some new function z. So we would like to consolidate the two and have a differential equation involving only one variable, preferably our new variable z. So what we're going to do is forget that this is here for a second, and let's just focus on the fact that z is equal to 1 minus y. What is z prime then equal to, or dz by dt? So I'm going to take this equation and then take a derivative of it with respect to time. The derivative of 1 is just 0. The derivative of minus y, recalling our implicit differentiation or simply the chain rule, you notice that the derivative of y is in fact just a derivative of y. We know it depends on t, so it will just be minus, which got inherited from here, dy by dt. Now, in this expression, I would like to replace dy by dt, so I'm going to work with this for just a little bit longer and rewrite this for dy by dt, not dz by dt. From this expression here, dy by dt, if I simply multiply both sides by negative, I will get exactly what I'm after, and I can see that dy by dt is in fact equal to minus dz by dt. I am now going to use this expression to consolidate my two variables here. So what I have is that dy by dt, which is the left-hand side here, is actually the same as minus dz by dt. So I'm simply going to replace it with that. The left-hand side here is minus dz by dt, and the right-hand side here is exactly what I called z. So this one simply gets transferred down as z. Now, was this whole thing worth the trouble? Well, let's take a look what we have here now. We've managed to transform dy by dt equals to 1 minus y into the equation that says minus dz by dt is equal to z. Or, if I would like to rewrite it for dz by dt, I'm going to have that dz by dt is simply minus z. Why is this so much better? Well, it's that much better because this is the equation of the form we have seen before. This is exactly the equation of the form y prime is equal to ky, where y is now just called z and k is equal to -1. So this equation I can solve. We've managed to transform an equation we did not have a solution for into the equation that we can in fact solve. We can solve this one. And recalling how this all works out, what we have here is that z, the solution, is some z naught, an initial condition, e to the power of the constant, which here is simply -1, times t. So z naught e to the power -t. Now, we started with the equation for y, so we would like to have a solution in terms of the original variable, which was y. So now that I have a solution in terms of z, I simply have to rework it back in terms of y. So I'm going to be replacing my z's with 1 minus y's everywhere I see them. So what am I going to have? On the left-hand side, I'm going to have 1 minus y is equal to z naught, which is going to be 1 minus y naught, e to the power -t. Now, it would be nice if I had this in terms of y equals stuff, not 1 minus y equals stuff. So let me rewrite that as that. So moving things around, I'm going to have that y is equal to 1 minus y naught e to the power negative t. And that's it. This is my solution to this original differential equation. Notice that we can actually generalize this process for any constants here. In this equation, I have essentially one here and one there, but nothing in the process was really attached to what the numbers are. So we can derive a more general solution to a more general differential equation. Here I have a and b instead of 1 and 1 as before, and here they're taken into account in the solution. So this is the second type of differential equation whose solution we're going to consider, and this is its solution. Let's practice for a couple of examples here how we can actually work this out. This is really basically a matching game. You're matching the differential equation to the one you're given, and you're going to produce the solution with the constants you're now handed. So here I have that dy by dt is 3 minus 2y. To make it easier to go through, you can, for the first few, write down the exact same differential equation on top just to see really what the a and the b are. And here I notice that my a is 3 and my b is 2. The one thing to be careful with is that this minus is built into the formula. So if you have a minus in your equation, this is the minus that's given, and b is actually the number in front of y. Once you have your a and b, you can simply plug them in into the general formula for the solution to produce the general looking solution. So what I'm going to have here is y equals a over b, or in my case 3 over 2, minus brackets a over b, which once again is 3 over 2, minus y naught, so that's an initial condition, and in this case we're actually given that y naught is 0, times e to the power of negative bt. Again, keep in mind that b is the value that is directly in front of y, with minus being actually part of the equation. So my b here is 2, so I'm going to have e to the power negative 2t. Now, of course, I can simplify this a little bit by getting rid of this 0. So overall, I have 3 halves minus 3 halves e to the negative 2t. I can check whether or not this is in fact a solution to this equation by taking a derivative of this and seeing if it satisfies this particular equation. And I encourage you to do so for extra practice, how to actually, first of all, check the solutions to differential equations and how to take derivatives of exponential functions. This is really great practice for that. Let's take a look at this next one. So I have y prime is equal to 3 plus 2y. So again, for the first few, before you get a hang of it, I recommend that you write the general form on top of it just to see what the a and the b are, because here it makes it very clear that a is 3, but b now has to be minus 2, because the general form has a minus inside of it. So a is 3 still, but b is now negative 2. And this will, of course, affect how you plug them into the formula. So in terms of the solution, I'm now going to have minus 3 halves minus negative 3 halves minus y naught. And again, hopefully that's something that's given to us, and it is here. So y naught is 1. So I'm going to have minus 1 e to the power negative bt. So b is minus 2. Negative of that is 2, so I'm going to have e to the power of 2t. And once again, of course, I can pull together the two terms inside the brackets here. So I'm going to have minus 3 halves minus 3 halves minus 1 is negative 5 over 2. With the negative in front is going to become a positive. So I have plus 5 over 2 e to the power of 2t. And again, I strongly encourage you to actually check whether or not this is true. So in both cases, take a derivative of this and make sure that that derivative satisfies this equation. In summary, what we have so far developed are two different solutions to two different differential equations. The first one was easy, so let's think about the formula and how this is represented on the graph. If I have this equation, dy by dt is equal to ky, or y prime is equal to ky, the solutions are going to be a family of curves, y equals y naught, the initial condition, e to the power of kt. So the curves will depend, their actual shape will depend both on the value of k, whether it's positive or negative, and the value of y naught. But we can sketch the general shapes and what they will look like. So for example, if I have positive y naught corresponds to, of course, the initial condition, so it will correspond to the y-intercept here. If I have a positive y naught and I have a positive value for k, then I'm in the case of exponential growth, and the solution curve will look like this. So this corresponds to y naught is positive and k is positive as well, which indicates growth. If y naught is positive, so let's say it's still this number, but k is negative, this will correspond to the exponential decay, because then the curve will look like this. So y naught is still positive, but k is negative, which will then represent the decay, right? E to the negative power will be a decreasing curve. The cases for y naught being negative will lie in the third and fourth quadrant when y naught is down here, and these are generally not going to be the cases we're interested in for applications, because no applications really have that the initial condition is some negative value when we're talking about things like population growth, radioactive decay, the spread of disease, and whatnot. This is the first type of the differential equation we've seen. The second one that we've just developed the solutions for in this lecture was this other linear type. So not only do we have a proportionality constant, we also have a fixed constant term. So the other way to rewrite this would be a prime is equal to a minus by, and we have just derived that the solutions to this equation were curves of the form a over b minus y naught e to the power of negative bt. Now let's take a look at this entire expression a little bit closer. There are a lot of constants, and so it's going to be hard to analyze in its entirety. But what we can notice is that the solution form will really depend on this exponential term, and in particular, what is happening in front of it. So the initial condition is something that is generally either given to me or we get to pick for analysis. What if y naught, this is going to be our first case that we're considering, what if y naught is actually equal to a over b? If I have that this term is equal to this one, then this entire bracket is going to be 0. 0 times anything is just 0. So this whole thing is gone, and I simply have that y is equal to a over b. It doesn't change, it always stays at a over b. This is what we call a steady state. If we were to graph it, this would be a particularly boring graph. A over b, the function will always stay there. Now, what about other cases? If we're interested in the case of equality, then we're probably interested in the cases on either side of equality. So either when y naught is bigger than a over b, or when y naught is smaller than a over b. Will this produce qualitatively different behavior? Let us see. First of all, the other thing that we have to think about is what happens to the exponent here. Is b positive or negative? So is my exponential actually decreasing like in the decay or increasing like in the exponential growth? And for the purpose of this analysis, I'm actually going to restrict ourselves to b being greater than 0, because this is where most of the applications are going to lie, with the equations that have the actual minus built in and b being positive here. If b is positive, let's think about what happens in both of these cases as t goes to infinity? So let me analyze this as t goes to infinity. In the long term, what happens to the population, or what happens in the disease spread as time goes on? If t goes to infinity and b is legitimately positive, then what I have in the power here is a negative number. E to the negative power, as the power goes off to infinity, approaches 0. So this term approaches 0. And then it doesn't matter what I multiply it by, the whole thing approaches 0, and y will once again approach a over b. Now, where the two cases will actually make a difference is when we're considering t approaching negative infinity. Then in one case, we're going to approach negative infinity, and in the other case, we're going to approach the positive infinity. However, again, in applications, t approaching positive infinity makes sense, but not so much when it approaches negative infinity. What we're going to do here is stick to our analysis of these two cases and draw two graphs as to how we can represent both of them graphically here. So as time goes on, y approaches a over b, which means that this is the horizontal asymptote here. So I can label this on my graph and sketch a little horizontal asymptote, and then think about what the curve will look like near it. If y is bigger than a over b, it means that my starting point is above the horizontal asymptote, but in the long term, my curve approaches the horizontal asymptote. If y naught is less than a over b, that means that I'm starting below the horizontal asymptote, but again, as the end behavior, approach the horizontal asymptote. So these are generally going to be my two cases. I can start at the steady state and then stay there forever, or I can approach it either from above or below in a continuous type of manner. Next time, we're going to see a few applications of both these equations and how these graphs can help us really grasp the concept of growth or decay.